In the first part of this programme, we looked at how we can take the simple things from the earth, the rocks and the minerals, the sea and the air, and get out of them the gases, the carbon dioxide, the oxygen, chlorine, salt, acids, alkalis, things that we can use to start making everyday things. We have to understand the way the molecules behave so we can use the chemicals in our fragile earth wisely and safely and provide your health and well-being. And so what we're going to do is we're going to start looking at the way we can use our understanding of the way the molecules behave to develop all sorts of new and exciting things. And we're going to start right back in the Stone Age, where if they wanted to paint a picture, they simply had to go out and find the rocks and the minerals and the charcoal that would give them the sorts of colours that they could daub on the walls. But by the time they got to the Middle Ages, they were discovering new things and the pictures were brighter and better. And you'll still find some of their paints in your paint box today. If you look, you'll see things like cadmium yellow and cobalt blue. But if you really understand the chemistry behind it, you can start making all sorts of different colours. These reactions are quite complicated, but they can change the colour. This yellow vanadium and zinc does something called a redox reaction. And you can see the yellow colour is already turning green. If you watch it, it will end up blue and possibly even purple. The iron can form a complex with this thiocyanate, which is very like the red hemoglobin in your blood in some ways, and hence the similarity in the colour. The bright blue copper here can be turned into a nice dark blue by making a complex with ammonia. And silver reacts with chromate, produce a red precipitate, and you can see the solid forming as the liquids mix. And tin can react with this orange dichromate, and this is called a redox reaction, and the tin makes the orange dichromate go green. And a combination of lead with iodide gives us, as you can see, a really bright yellow solid. And it's reactions like these where we really understand why and how the colours occur that allow us to produce all the paints, pigments and inks that you see on glossy magazines, and all the bright colours on the books and things that you read. And just imagine what it would be like if you didn't have all this colour on things like advertising and in the books you read and learn from to make things look more interesting and more fun. That's one of the ways we can develop our knowledge and use it to make life more like every day than the Stone Age. Mike's going to show you how our understanding helps us to invent other things and control the reactions.
It's understanding what molecules are like and how they can behave that enables us to control the reactions that they do. And one way of illustrating this is to take some metals that don't appear to want to react with oxygen when we heat them in this form. A solid lump of iron or aluminium will not react with the oxygen in the air because the particles can't mix. If we make the particles mix more efficiently with those in the air, we do get an obvious reaction, and this is the sparkler effect that you get with iron powder. If we do the same kind of thing with aluminium, which didn't react at all in the first instance, now it's a very fine dust, its particles can mix very, very efficiently with the particles in the air, and we get an instantaneous and rapid bright reaction. Now, one way of getting things to react is to make their particles collide together more often and to mix well. Another way is to give them an awful lot of energy. And if that happens with aluminium, even in its solid form, a disaster like this can occur. Now, as I'm sure you're aware, one of the unfortunate consequences of the Falklands conflict were that some of the Royal Navy's ships were hit by missiles. Now, a substantial proportion of those ships were made up out of aluminium, and the heat from the missile was enough to produce the kind of energy to get the reaction between aluminium and oxygen occurring. Another way we can get particles to mix and react is to take solid materials, where, as I've said, the particles are locked up and aren't free to move, and turn them into a liquid, not by melting them, but by dissolving them. Now, we've got two chemicals here. One's a reactive metal, magnesium, and one's the compound of a non-reactive metal, silver nitrate. And if I mix these two solids together, provided there's no water there, and I hope for the moment there isn't, there's no reaction at all. If we make the particles mix together, by adding some water, it'll dissolve the silver nitrate, and hopefully you'll see a fairly vigorous reaction.
That is a reaction where, because the particles can move, it suddenly takes off. And so it's all to do with the collisions between numbers of particles. And I want you to help me see this again, because in this flask I have got twice as many particles, molecules, as I have in this one. So this one will go quickly and this one will go slowly when I mix the chemicals. So when I say ready, steady, go, I want you to start counting. All right? Out loud together. All right? Ready, steady, go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
You see it change at 13? This one has got double the number of molecules in it, so it should go faster. So you're going to count this one, and because it's double, you should see that the speed is exactly related, right? When I say so, ready, steady, go.
1, 2, 3, 4, 5, 6, 7, 8, 9.
So we have 13 and 8, which is about the 1 to 2 ratio you'd expect on the number of molecules. And that shows you the sort of idea of the control we can get. Solids are very slow because they're not moving around. Liquids are faster and we can control them by the amounts there. So what about a gas? Gases, we've shown you, are on the move. And that means when I break this balloon, and if you blink you'll miss it, so watch carefully, you'll see the hydrogen in this balloon reacting with the oxygen in the air. You'll actually see it burn, but it's very, very quick.
Now, as Anne's shown you, that gases, when they react, can combine very, very vigorously and give rise to explosions. Now, luckily, we don't come across hydrogen in everyday life, so it's not really a hazard. But the natural gas that's pumped into your homes is a hazard, as I'm sure you're aware. Normally, you see it burning in a relatively controlled fashion, rather like the Bunsen burner here, but it can explode given the right conditions. In the bottle here, to give you some idea of the proportions, I've got so much natural gas and the rest is oxygen. And I'm going to show you what happens when it burns. Now, if you scale that up by a factor of approximately 10,000, you'll get some idea of the nature of gas explosions in domestic situations in buildings. And it won't be at all a surprise that you can devastate a building and bring it tumbling down with a gas leak. When it mixes with air in the right proportions, you get this kind of problem. You can harness these vigorous reactions involving gases so that the energy just doesn't get wasted. You can turn it into movement. And that movement can be used to drive a car engine, for example. The petrol and oxygen mix together, they burn, and the explosion drives the piston up and down in the cylinder. Another way we can demonstrate chemical energy being turned into movement energy is to show you an example of rocket propulsion. Here we've got a mixture of air and hydrogen, which you've seen burn vigorously together. We can use the energy of that reaction to drive the rocket through the air.
And if you think about it, launching rockets is very important to you, because your telephone call to Granny from Australia or somebody on the other side of the world depends on the satellites being up there to transmit it. And our pictures that come to watch the Olympics, and our ability to send men to the moon or probes out to Mars or Halley's comet depends on being able to launch rockets. There's a problem though, because when you launch a rocket and it the fuel burns, there isn't any oxygen around to make it burn. So you've got to have a chemical reaction that will take off without the need for a spark or a splint. You need something that can go without the oxygen. And I'm going to show you a reaction which doesn't need any sort of energy to start it. It just goes. It's what a chemist calls a reaction with zero energy of activation. And when I add the fuel to the chromium oxide, you see, it burns, no problem, we don't need a match. And that's the idea we need if we want to launch a rocket. Now, I don't want to send you all to Mars or the Moon this afternoon, so we've got to be a bit careful about the reaction. But this reaction is the type of reaction that they actually use to launch a rocket. This is the sort of thing they use as rocket fuel. We've got nitrogen dioxide. If I had hydrazine here, you'd all end up on the Moon. But I don't think we'll do this. But just to show you how vigorous a reaction this is. And on a large scale, that would be able to launch a rocket. That's the type of reaction we would use. Knowing why and how these reactions occur is very important. They're great fun to do things like explosions, but you should never ever try any reaction unless you know exactly what's going to happen and you can do it safely. Because not only do we want to discover new and exciting things, but we want to make sure that we can do them safely. And when you can, then learning how to discover new ones and do reactions like that is all part of the fun of chemistry. The world has another resource. It's the remains of complex molecules that were built up millions and millions of years ago and are now left as oil. And it's a real treasure chest of molecules. If you get the oil from out of the North Sea or from the deserts and you know what you're doing, you've got the skill and the imagination of chemists, then you can invent all sorts of new and wonderful things. And I want you to look at these things I've got here in front of me and just imagine what it would be like if you got up tomorrow morning and there wasn't any toothpaste. And you say, oh, that's all right, I've just forgotten to clean my teeth. But supposing in a week or a fortnight there still wasn't any toothpaste. Or you went to the doctors because you weren't well and they didn't have any medicines to make you better. Or you had to go to hospital for an operation and they didn't have an anaesthetic because the chemicals that provide these things for you, all the things I've got sitting in front of me here, come from the oil. You think what food would be like if it had to be sent round the country without being protected from flies and dirt and couldn't be sold in a nice, clean sort of way. And that's because all these molecules come from oil. And it's about using the fairly simple molecules in oil and building them up to make complicated things.